Welcome to The Explainer. Today, we're going to dig into a really core concept in chemistry, how energy is kind of the hidden force driving every single chemical reaction.
Let's kick things off with a simple question. Have you ever used one of those hand warmers and thought, how does this little pouch just create heat? Or snapped a cold pack and felt it turn instantly icy? What is going on there?
Well, the secret is all in the fascinating world of energy and chemical reactions. And getting a handle on this is absolutely crucial, not just because it's cool, but because it's a huge topic for your WAEC, JAMB, and NECO exams. So here's what we've got lined up to get you completely ready. First, we'll cover why reactions even have temperatures. Then we'll look at giving heat versus taking heat. After that, we'll jump into how chemists do the math. Then the fun part, solving real exam questions. And we'll finish up with a quick recap of everything you need to know. Okay, let's dive right in. To really get why a reaction can feel hot or cold, we need to figure out where this energy is even coming from. And the answer is, it's all locked up, stored inside the chemical bonds themselves. Now, chemists, of course, have a specific name for this change in heat. It's called enthalpy change, and we show it with the symbol delta H. This is a big one, a key term you've absolutely got to remember. The easiest way to wrap your head around it is to think of it like a business transaction. Is your reaction ending with an energy profit or an energy loss? Delta H is just that bottom line. It's the energy of your final products minus the energy of what you started with. Simple as that. All right, so this whole idea of an energy profit or loss, well, it neatly splits all chemical reactions into two fundamental groups that you need to know inside and out. So on one side, you have your givers. These reactions give heat away to their surroundings, and we call them exothermic. On the other side, you have the takers. They take heat from their surroundings, and we call them endothermic. Givers feel hot because they're literally giving heat to you. Takers feel cold because they're taking heat from you. Let's zoom in on exothermic reactions. Because energy is exiting the system, the stuff you end up with, the products, has less energy than what you started with. That means the change, delta H, is a negative number. The most classic example is burning anything, like methane in your gas cooker. And on the flip side, you have endothermic reactions. They have to pull energy in from the outside world to even happen. This means their products have a higher energy level, making delta H a positive number. And the single most important endothermic reaction for all of us? Photosynthesis. It's how plants use the sun's energy to make food, literally fueling almost all life on Earth. Okay, so that's the what. But what about the how? How do chemists actually figure out these energy numbers without having to run every single experiment? Well, they've got two incredibly powerful tools to do the math right on paper. The first tool is Hess's law, and it's a fantastic shortcut. Imagine you're hiking up a mountain. Your total change in elevation from the bottom to the top is the same, right? It doesn't matter if you take the short, super steep trail or the long, winding path. All that matters is your start and end point. Hess's law says chemistry works the same way. All right, let's really put this into action and walk through this example together step by step. Our goal here is to find the delta H for making methane. So look at step 1. We need methane as a product on the right side, but in the reaction we know it's a reactant on the left. So what do? We just flip the whole equation around, and this is the crucial part. We also flip the sign of its delta H from negative to positive 890. Easy. Now for steps 2 and 3, we just add in the combustion reactions for carbon and hydrogen. But wait, we need 2 hydrogens, so we have to double its delta H value. Finally, step 4, we just add it all up. The other chemicals cancel out, and we sum up the numbers. Positive 890 minus 393 minus 572, which gives us our final answer, minus 75 kilojoules per mole. See, it's like a puzzle. Our second tool takes a totally different approach. Instead of looking at the whole reaction, we're going to zoom way in, right down to the individual bonds holding the atoms together. Every single one of those bonds has a specific amount of energy, and we call that its bond energy. And you know what? The formula for this is actually super straightforward. A chemical reaction is really just two things happening. You break old bonds, and you form new ones. That's it. So the total energy change is just the energy you had to spend to break all the old bonds, minus the energy you get back when all the new ones form. Okay, theory is one thing, but you know what really matters? Seeing how this stuff actually shows up on an exam. So let's get our hands dirty and tackle some real questions from past JAMB and NECO papers. Okay, here's a classic from a JAMB paper. This one connects enthalpy, or delta H, to a couple of other ideas, gives free energy, or delta G, and entropy, or delta S. Now don't panic. The key thing to notice here isn't just the formula that connects them, but the units. Always check the units. And right here, this slide shows the #1 most common trap students fall into. I see it every year. You see the temperatures in Celsius? That's a trick. You cannot, under any circumstances, use Celsius in this formula. You have to convert it to Kelvin first. Just add 273. It's a tiny step that is the difference between getting the whole question right or getting 0 marks. All right, let's switch gears to a NECO question. This one has no math at all. It's a test of pure understanding. You dissolve some ammonium chloride in water, and the beaker gets noticeably colder. So what does that tell you? Is the process exothermic or endothermic? And yep, this is another classic exam trap. Your brain might hear cold and think it's giving off coldness or something. But think about it. Why does it feel cold? It feels cold because the reaction is literally sucking heat energy out of the water and out of your hand to make itself happen. It's taking heat in. And what do we call a process that takes heat in? Endothermic. Okay, deep breath. We've gone through a lot. So let's use this last section to really lock in the key points, the stuff you absolutely need to have crystal clear in your head for exam day. Think of this table as your ultimate cheat sheet for revision. It lays it all out, side by side, no confusion. Exothermic releases heat, has a negative delta H, and feels hotter. Endothermic, it's the total opposite on every single point. Absorbs heat, positive delta H, feels colder. And before we wrap this up, let me leave you with my top 5 tips. These are the little things that'll save you from losing easy marks. #1, always balance the equation before you start. #2, watch those positive and negative signs like a hawk. 3, don't forget your units. 4, label your diagrams perfectly. And 5, I'm gonna say it one more time, always convert your temperatures to Kelvin. So I'll leave you with this final thought to chew on. We've talked about little hand warmers and photosynthesis in plants, but now that you understand the energy behind them, think bigger. Think about a car engine, a rocket launch. Think about the sun itself. It's all just chemistry. It's all just energy-changing forms. Pretty amazing, right? Thanks for tuning in.